We're going to finish up chapter 18 today. And we're over here. And it's all about lithium aluminum hydride here. This is not quite exactly the same as the one I left you with before break. I added this guy down here. And I put some section numbers in to help you study. So you got to remember, every time you see lithium aluminum hydride, you do the same mechanism. So here we go. 1, 2, 3. 1, 2, 3. Program yourself just to do that every time you see H with ALH and a 3 and a minus. And you get an H minus plus alane. Seriously, that's his name right there. Alane. Well, thought I could do a fast one and copy paste, but you know, you guys gotta draw it, so why shouldn't the teacher have to as well? Alane. Okay. What's H minus interested in? Well, it's got a minus charge. Minus charges are interested in plus charges. The plus charge of the ester will react in both, in this one, and the ketone will react as well. Which one's more reactive? Well, I wouldn't grade you in this course on knowing that, but a ketone is a little more reactive than an ester. You'd say, wait a minute, Dr. Whitaker, you said H minus is attracted to plus. Wouldn't this be a stronger plus because it has 3 bonds to O compared to this one, which has 2 bonds to O? You have a nice argument there, but you're neglecting the fact that this carbonyl that has a delta plus here, delta minus here, is resonating with the oxygen over here, and that profile is changing all the time. So the carbon is not quite as reactive because the resonance stabilizes it. Oh, it's got resonance with lone pairs on this O resonating up to here and back. Once again, I'm not going to grade you on that. There are definitely 2 reductions happening here. You can tell in the product, right? Where are all the new H's? Let's put them in. H's from H minus are green. So I'm recoloring my H minus green here. And since it's reacting twice, I can tell the viewer, it'll be red first and it'll be green second. So the H minus is attacking the ketone first. And another H minus is attacking the ester first, but not as fast, so it would be second. Okay, same story everywhere. Oh, we only have 1 carbonyl here. Looks like the same thing every time, huh? Oh, no carbonyl here. Take a wild guess what the H minus attacks down here. There's a carbon with a positive charge because it has 3 bonds to more electronegative nitrogen. That's positive. That's why we're attacking the positive. All right. Now, when we're up here, this has a leaving group on it. An ester has a leaving group. It's not a great leaving group, but it's a leaving group. So a third step would be to resonate and kick off the leaving group. And that definitely is after red and green, right? Even if I don't write anything, right? Because it's not red or green. It's got to be third. And I think that's the only one that's got 2 reactions going on. We can't do I yet because we don't know about this guy. So let's write down our results from the things we've done so far. We're going to have the carbon in black, with an O minus here, CH2, carbonyl still here. That's an aldehyde, and O minus ET here. So that's what we have after all those shenanigans up there. And here, I'm going to do a little extra on this one. Do you know why I am doing this on this one and I didn't do it on the other ones? It's a good question. I would have accepted it on the other ones too, like where you see an O minus over here. You could have attacked LiAlH4, and it's probably what happened. I see. I heard some things I wanted to hear from the lady in front here, but she said something that I want her to think about again. She mentioned NH2 and leaving, but look carefully. NH2 does not leave. I don't want it to leave. That's why I'm making the O so it can leave with something. Otherwise, well, I do see the aluminum ends up with O here. So you guys want to make your life easier and just do it here too? That way you're learning just the same thing over and over. I don't mind. This would be purple. I don't even know. Something else different. And that would change this to be LiAlH 3 times. And that's a minus, right? And no charge. And it's going to look a lot like this one over here. O with Al, 3 H's, and a minus. And then don't forget the NH2 here. Pushy, pushy. And what are we going to get down here? You know, you guys don't have a lot of room to play with, but we don't need a lot of room down there. And that's a minus. Well, you know what? I want to be consistent. I'm going to make your guys' lives more consistent. If there's no leaving group, always attack the aluminum. If there's no leaving group, always attack the aluminum. And now we got our aluminum on here. And you've got an aluminum with H's and a minus charge. And clearly we need new H's here and here. Here and here. Here. And oh, I got news for you. There's a mistake. I did do this as a last minute rush job because I thought it fit here. But the nice thing about that chemical, which we haven't even talked about yet, is it will not touch a ketone. So that ketone needs to be unadulterated, as they say. Right there. It's still the same ketone. It did not react. The only new H is that aldehyde H there. So looking forward to a simple mechanism in there. So fix it so that's a ketone. I just did a copy paste job from up here, and I should have thought a little more. All right, are we anywhere near done? Heck no. This could be a double activity. We need more H minus. And look at all the products. There's never aluminum with 3 H's when we're done, right? It's always aluminum with 2 H's. So we're going to be generating H minus again. And H minus here. You guys tell me what you think H minus is going to do. H minus loves attacking carbonyls. Any carbonyls left in the first one? Yeah, let's do it. In fact, that's all you've learned, H minus attacking carbonyls until now. Well, still no carbonyl in the next one, so let's just draw, well, let's look ahead too. Oxygen's got to go in number 2, right? Oxygen's got to go. There's no oxygen here. Nitrogen is got lone pairs, makes it pushy because it's not like oxygen. It's less electronegative, so when it has a lone pair, it likes to push, resonate. It can push off even mediocre or bad leaving groups. We have seen this before. Not new. You're kicking off O minus. O minus. Why don't we draw it this way so it's quite easy to see how close you are on the aluminum. H2AlO lone pair minus. I think you can see where that piece is coming from. And we have an iminium here. Iminium. That is going to behave a little like an aldehyde with H minus. An H minus with an aldehyde, like right here. There. Whoa, 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 whoa. Dr. Whitaker, nobody said anything here. You guys are so nice to me. You forgive me. I was saying H minus attacking aldehydes and ketones, and I used an O minus. Oh, wow. That O minus is going to be HOET when we add HCl. Some of you probably knew that already. My apologies. That was just whack, as they say. There's your H minus attacking. There's your H minus. This H minus here is going to, the reason I brought it up now is I was going to do what I did over here, and I realized what I did over there was crazy. Here's H minus, and it's going to do the same thing here. And guys, I think the nitrogen molecule's done. Look, second H minus is needed, right? Here it is. Coming in hot. That part's done. I wouldn't even grade you if you forgot to do the HCl on this thing, because isn't this a side product? How picky am I on those? I'm not really. So maybe I'll show it on one of them and not on the other. Yeah. So here's O minus. I'll show the HCl here. Step 2, remember you can't do any step 2 until all that other stuff's done. There's your HCl. At least we have HCl doing something here. So like that arrow crossing over like that. O minus grabs H. Cl gets lone pair. End of story. H2AlOH. We got our amine. So a nice way to make amines is from amides. And amides are pretty easy to make. We did those last day, which was a long time ago now. Okay, so we got that one done, and this one's pretty darn close. What's this one he's talking about? Here, this one. You got your O minus. You've got your O attached to AlH2. And I would have to say, which of those two O's looks more reactive for the HCl step? You got to pick the one with a minus, right? Yeah. So protonate it first. Step 2, you're finally doing step 2. And in green, this one, Al2OH. Well, the O is really, you know, I'm just going to go like this. And I'm going to go like this. Ooh. Looks like I got rusty over break, huh? Forgot my second arrow here. Here's the second arrow here. And I guess your aluminum looks more like this if you do it this way. It's kind of like a Lewis acid there. Water would probably attack it because HCl is almost always aqueous. Cl minus could attack it. I don't care. It's a side product. How's that? And what about this next guy? This next guy. What do we have here?
The side product ALH3.
This one's got 2 H's because we got rid of the third here.
But they grabbed the H from HCl. Right?
Oh, no. Where did that H go from HCl? The H in this bond, which of the 2 atoms would keep the electron? The O, because it's more electronegative. So it kept the electrons and used them to make a bond to H. So that new H, that is this black H here, is this H right here. And aluminum just says, I can't compete with oxygen, so I just lost electrons. I'm a cation now. And does that finish that guy? It does. And I was starting to talk about this guy, but here he is. And we got our aluminum with 2 H's. And we have an H minus. And we're hitting it. There's your second H. Almost done, and you're hoping we're almost done. And minus. And step 1, baby blue. Step 1 is HCl on the nitrogen. And step 2 would be HCl on the nitrogen aluminum bond. Oh, don't do it in red though. Green. So your second H also comes from HCl. So nitrogen gets 2 new H's. One's just acid base that's red, and then it's kind of an acid base that's blue, and you guys are also puzzled about this story down here again. Kind of the same as before. And it's a side product. There are probably other things going to happen to it, but it's a side product. I do not care. We have another NH2. I had an H attack here, so there's the first H. I didn't show it, so you might have missed it. That's a new H. And then the new H went here. So there's 2 H's. Those would be the green ones, right? And our new player in the game here is DIBALH attached to a hydrogen, which is diisobutyl aluminum hydride. And it is nowhere near as reactive as the other hydrides on this page because it doesn't have an anion, does it? Neutral. It only has 3 bonds to aluminum. And I think you know what IBU stands for, right? Isobutyl. So it's kind of bulky. And it only likes the ester here, which is interesting. Remember before I said ketone's going to react before ester? I did. I didn't make that up. With lithium aluminum hydride, that's the story, because H minus attacks the most positive thing that's not resonating away in stability. But with the ester, for reasons that are, this is beyond what you're responsible for. One of the O's forms a complex with the aluminum and makes the H more negative, and it attacks intramolecular. And you don't have that, it's called a chelation factor. It's a lot of lingo we're borrowing from other chemists. And you don't have that going on with ketones. So in this case, this aluminum species is less reactive towards a ketone. Kind of cool. And the mechanism is pretty straightforward. The H does go to the carbonyl. We resonate up. And then the electrons do go back. And well, let's just do it this way. Let's do it that way. So that's step 1. I think your textbook has an overly simplified version of this. If you want to use that one, I will accept it because it's in your textbook. This is probably more realistic. We got Al. What the heck? Let's draw those 2 isobutyl groups just for old time's sake. You got a new H here. And you got a leaving group. And then what happens during the HCl step is you get this. Let's resonate. Let's have this attack HCl. I don't know why it's in purple. Resonate. Attack HCl. And these guys can just attack the, there you go. This time I'm going to try to go towards that product I see. This got chlorine on aluminum this time. Okay. What you got? Got a carbonyl. Whoa. Carbonyl. We got aldehyde with an aluminum species on it. IBU2. And that's now 4 bonds because it's got a Cl as well, right? And this thing just does this. And you're done.
Did you think of taking the electrons of hydride and making it into a hydride ion?
Yeah, except we don't really see a hydride ion. She was asking, is this the same as making a hydride ion like the other 3? And it wasn't quite. We never see the hydride in this one. This whole piece ends up saddled beside this piece, and the H is attracted to that, and the bond of aluminum's happening at the same time. It's like they're beside each other, just doing a shuffle of electrons like that in a circle. And you get an aldehyde. This is a nice way to make aldehyde from esters. So what do you remember about DIBALH? You can take an ester and make it into an aldehyde. And what about this ester here? Became a primary alcohol. Same up here, primary amide, primary amine. And nitrile became a primary amine. Amines, very important. Pretty much our last big functional group for all of organic chemistry. Nitrile didn't look like nitrile. There you go. Didn't save this at all. Okay. So there we have a nice double activity to start our post-break continuation of the semester. Stay tuned for more.